All right. So, we will continue our discussion related to the transport phenomena. So, in the last class I hope you recall, it has been quite some time now, you recall the assumptions that we made in order to derive the equilibrium constitutive laws. So, basically we have to start from the non-equilibrium distribution function, and but the fact here is, since we are deriving continuum laws, we can make some approximations. So, one of that is the deviation from the equilibrium distribution function is quite small, that okay. So, that is in one way when you look at the quantity t by tau, okay, if your relaxation time is quite small, that means this t by tau is quite large, which means that the non-equilibrium will quickly relax to the equilibrium, or the deviation between f minus f naught will be very small, because f minus f naught is proportional to e power minus t by tau. Okay. So, therefore, when you are looking at continuum, so you can make safely this assumption that f minus f naught is quite small, and we are calling this by another distribution function g, which measures the deviation from the equilibrium, and we assume that this is small compared to f equilibrium itself. Apart from that, also we have to make sure the gradient or derivatives of g in whatever spatial direction or momentum plane, so should be smaller compared to the corresponding derivatives of equilibrium distribution function. So, with these assumptions, when we substitute for f in terms of g and f equilibrium into the BT, and we can knock off certain terms including the unsteady terms. Okay. So, we can assume that to derive the constitutive laws, you do not have to consider a transient process. So, just a steady state should be sufficient, and also with these assumptions you end up with the reduced form of the Boltzmann transport equation. So, which connects your non-equilibrium distribution function as a function of f equilibrium, right. Now, we can start applying this to different systems. So, first if you want to apply this to phonons, okay. So, we can derive the Fourier's law. So, therefore, in the case of phonon transport, it is only transporting heat, and there is no electric field or external forces acting on the energy carrier. So, therefore, the change in momentum will be 0. So, we can neglect the derivatives with respect to the momentum plane, right, and therefore, we have only one derivative in the physical space, okay, which is actually you can express in terms of a spherical coordinate system. Okay. So, now we consider one dimensional transport of heat, and we can write down the expression for heat flux along the positive x direction, and suppose you know what is your non-equilibrium distribution function, and you know the energy of each quantum state h bar omega. So, we can calculate the heat flux as the corresponding energy times the velocity in that particular direction, right, and we can, therefore, this will be the component of energy flux for one quantum state. So, we can sum this over all the quantum states, okay, kx, ky, kz, and divide it by the volume to get the units of heat flux watt per meter square, right. So, this is similar to the statistical equilibrium case, except there we were finding out the internal energy, and we were just doing the summation over all the quantum states, and we use h bar omega times f equilibrium there. Okay. So, now for the flux we have to also consider not equilibrium, but non-equilibrium distribution and multiply by the corresponding velocity. So, this is the basic principle, from which now we go on the further mathematical details, which include conversion from the discrete summation into an integral function, and to do this we now resolve the quantum states into a 3-dimensional spherical coordinate system. So, these discrete quantum states are supposed to be contained within a huge sphere, the sphere of radius from going from 0 to infinity, okay, huge solid sphere. And therefore, if you take one solid angle, the area that is subtended by the solid angle, so we can write down the corresponding relation between the area or the volume and the corresponding dkx, dky, dkz. And when we do this conversion, so I think we already did those things in the last class. So, we can finally write down in terms of quantum states, we can replace them in terms of density of states, okay, and which now looks something like this. Okay. So, therefore, we started from a discrete summation over all the quantum states, we replace that with a integral over all the quantum state spherical coordinate system, and from there we use the concept of density of states to convert the momentum k into the energy or frequency omega. And finally, therefore, we have converted the k space or the momentum space into a physical coordinate space which is subtended by a sphere and the corresponding frequency space. So, therefore, we have 3 integrals here in place of kx, ky, kz. So, 2 integrals, one with respect to the polar angle theta going from 0 to pi, and the other is the azimuthal angle 0 to 2 pi. So, this will make a complete sphere, and the third integral is over the entire frequency space. So, 0 to omega max. So, these are all the finer mathematical details, and from this point we now substitute for the expression for non-equilibrium distribution function f, which we have now written cast in terms of f equilibrium. Okay. So, therefore, now this is going to be much easier to integrate, okay, since everything is in terms of f equilibrium, and therefore, finally, we reach this particular expression here. Okay. Now, what will be the integral 0 to pi v times cos theta into f equilibrium into sin theta d theta, okay, and again integrate 0 to 2 pi d phi. Okay. So, f equilibrium is actually uniform over theta and phi. So, it does not change with respect to theta and phi. F equilibrium is only a function of temperature, right. If you take the Bose-Einstein distribution function, it is a function of what? Omega and temperature. So, there is no dependency on, therefore, directional space. So, it is uniform over the entire direction. So, that is why I plotted f equilibrium as something like this, it is uniform. Okay. So, therefore, when you have a uniform distribution and you integrate, you multiply that with cos theta. Okay. So, therefore, what happens about the y axis, this is going to be, so this part is going to be cos theta will be, yeah, so totally it will be 0. So, f equilibrium cos theta on this side, so this is from let us say 0 to pi by 2, right, and this is from pi by 2 to pi. So, our definition of theta is this, correct. So, therefore, when we say cos 0 to pi by 2, so in that it will be positive, pi by 2 to pi it will be negative, and it will be symmetrical about the center line. So, therefore, if you multiply f equilibrium cos theta, so this is going to be 0 to pi, it will become 0. Okay. So, therefore, this entire term, this f equilibrium term will vanish. You understand? Is that clear? So, f equilibrium is constant here, independent of theta and phi. So, therefore, if you just say integral cos theta from 0 to pi, so 0 to pi by 2 is positive, pi by 2 to pi is exactly negative, the same magnitude. So, this will be just dropping off. So, it will be 0 and therefore, we end up with simply 1 by 4 pi 0 to omega max, we have d omega and 0 to pi. So, we have tau into, so therefore, this term is going to go away, we have v into v square, okay, and we also have cos square theta sin theta d theta. Okay, so, we also have h bar omega, and we also have this term right here, which is df equilibrium by dt, and dt by dx can now be pulled out of the integral. We can write this outside here as dt by dx. This is independent of your directional space and frequency, or for a particular case we maintain temperature difference. Okay. So, then this is therefore d theta here, and when you integrate d phi, so the dependence 0 to 2 pi d phi is just 2 pi, right. So, therefore, this becomes 1 over 2. So, 2 pi in the numerator and 4 pi in the denominator, this becomes 1 over 2. Is that clear? Is that okay? So, now we have integral in terms of theta and omega. So, you can evaluate this integral with respect to theta. So, that is basically 0 to pi sin theta cos square theta d theta. This is what you have to evaluate, and if you do this, you will get this is equal to 2 by 3. Okay. So, you have to use cos square theta is 1 plus cos 2 theta by 2 into this, and then you will be able to find out this integral. Okay. So, therefore, your q x will become minus 1 by 3 dt by dx 0 to omega max d omega tau v square. Okay. Now, I can take h bar omega just inside this term d by dt. I can write this as h bar omega f equilibrium into d omega. I missed a d omega here, there should be a d omega here. This is your density of states, right. Right. Okay. So, therefore, now anybody recollect what is this? I think you should be able to recollect. So, this is your volumetric heat capacity. Is that okay? You go back and check. So, the simplest thing h bar omega into F equilibrium, what is that? Energy of a single quantum state. Okay. So, if you therefore integrate it from 0 to omega max h bar omega f equilibrium d of omega, that will give you the internal energy, total internal energy of that entire system. So, du by dt will be your volumetric heat capacity. So, therefore, here what we have written d by dt of h bar omega f equilibrium d omega is the volumetric heat capacity of a single quantum state, of single frequency, right. So, if that is integrated over all the frequency, that will be the total volumetric heat capacity, you understand. Okay. So, therefore, this is nothing but we can write this as Cv within bracket omega. Okay. So, this is a micro, again a micro state heat capacity, you understand. If you integrate this over all the micro states, that will give you the macro state heat capacity. Okay. So, therefore, why I am doing this is because this is a function of frequency. Okay. So, and you get tau and v also, tau for example could also be a function of frequency. So, we cannot simply assume tau and v as constant and take them out and then simply write this as c. We can sometimes do that for special cases. For generic cases, the relaxation time is also a function of frequency, because if you go back and see the different kinds of scattering mechanisms, we have talked about phonon scattering. So, for example, the Umklapp scattering is a function of frequency, and same way the impurity phonon impurity scatterings, right, that is similar to your Rayleigh scattering. It is a function of frequency to the power 4. So, therefore, in all these cases tau is also a function of frequency, and we cannot simply assume this to be a constant. So, therefore, we can write this as 1 by 3 dt by dx 0 to omega max d omega tau v square c omega. Okay. So, this is your final expression, and so this is your Fourier's law in fact. Right. If you know how to identify the expression for conductivity, this is your Fourier's law. So, where conductivity K will be one by 3 0 to omega max, you have tau v square c of omega d omega. So, if you express this integral with a quantity called thermal conductivity, then this becomes your Fourier's law. So, therefore, now you get your minus k dt by dx. Okay. So, in this case we introduce quantity called thermal conductivity now, which is basically related to your relaxation time, your phonon velocity and your specific heat capacity for a given microstate. If your tau and v are assumed to be constant independent of omega, okay. So, then this can be simply taken out and this can be written as 1 by 3 tau v square c v, that is it. Or in terms of mean free path, So, how can we write in terms of mean free path? 1 by 3 Now, go back to your kinetic theory expression, what we derived from kinetic theory, which we called as an approximate way of deriving, and compare this expression with that. So, what do you find from a kinetic theory? Same, correct. So, there however, the more accurate expression is what? This one. The kinetic theory cannot basically predict this, it only predicts this. That is a case where your relaxation times are frequency independent, but nevertheless it gives a very good order of magnitude prediction. So, we derived the same expression from kinetic theory. So, we considered one interface, we considered the flux of the phonons travelling in the positive x, flux of phonons travelling in the negative x, therefore, net flux, and from that we have determined the expression for conductivity, which turns out to be the same as the frequency independent case, right. So, therefore, the more rigorous expression would have been this one. So, we have therefore now shown that what we call as Fourier's equation, although people call this as a constitutive relation and hypothesis in the macro scale, you should understand that they are not really hypothesis, but can be derived from the subcontinuum equations. Okay. So, in the subcontinuum we do not have to define a property like conductivity. Okay. So, it is all function of the phonon velocity, relaxation time, heat capacity and so on, but we can relate all this to the thermophysical property called conductivity, and therefore, we can say that this is your Fourier's law, correct. So, the same, this is a very useful way of deducing many constitutive relations. So, not only the Fourier's law, but we can also do this, for example, to deduce the Ohm's law. Okay. So, maybe to just give you another example. So, let me do this also for the charge flux similar to the heat flux here. So, the electron charge flux. So, we will also now use this to derive the Ohm's law. You can also use this to derive the Newton's law of viscosity in the case of molecules. So, there the F equilibrium will take the form of the Maxwell-Boltzmann distribution, which is a continuous distribution. So, you do not have to do a summation there, everything is a continuous integral. So, all this conversion from summation to continuous space and then converting that to density of states, all those things are not required. So, it becomes much simpler to directly deal with the Maxwell-Boltzmann distribution. But let us look at the case of Ohm's law. So, probably you can start with the basic steps are similar. So, the way we are going to find the flux, except that instead of heat flux we will have the current flux, right, and therefore, instead of h bar omega, so we will have the charge of an electron minus E. Okay. The rest of the procedure is similar, you have to multiply the non-equilibrium distribution function to the corresponding charge, corresponding velocity, that is the charge flux, which is your current flux. Okay. So, therefore, similarly you will be doing the same conversion, you can do that again from the summation to continuous integral and use that density of states, except now you are dealing with electrons. So, instead of omega you will have d as a function of energy E, right. So, density of states for electrons should be used, and again when you substitute for F in terms of F equilibrium, now when you have a charge flux or current, you have associated electric field. So, therefore, this term will not be 0, correct. So, you have a electric field, you have a corresponding force. Now, that force is called the Lorentz force, that is due to the electric field and the flow of electrons. Okay. So, the electrostatic origin is the Coulomb force, the electrodynamic flow is the Lorentz force. Okay. So, you substitute F in terms of So, how do you relate your electric field and F? Minus E, Q is the charge which is minus E times capital E, capital E is the electric field. So, this will give you the Lorentz force. Okay. So, just substitute that and you therefore come to the expression till somewhere here. So, you will have an expression in terms of density of states and then substitute for F in terms of F equilibrium. So, can you all attempt that? So, exactly the same similar system, but instead of flow of phonons we have flow of electrons and they are transporting charge, not heat. Okay. Now, in a real conductor, the electrons will, semiconductor or metal can do both, it will transport charge flux as well as heat. Okay. So, from the generic thing we will make an approximation, specific approximation here if you are considering only charge transport, the other things, and then we will, but till that point can you all start? So, therefore, to derive the Ohm's law you can assume that the entire metal or semiconductor material is isothermal, there are no temperature gradients. If temperature gradient comes in, then again you have simultaneous heat transport also along with the charge transport. Okay. So, therefore, to derive the Ohm's law you can assume isothermal metal or semiconductor. So, therefore, how do you write the relation between F and F equilibrium? First step. So, F will be equal to F equilibrium minus tau into Vx, and then you have, let me go step by step. So, I have tau, and the first term is Vx times df equilibrium. We have the charge transport only in the x direction, we will assume. Okay, therefore, df equilibrium by dx. You do not have gradients in the other directions. Okay. So, these are very subtle points now. See the way we have done the phonon transport. We have written this gradient in terms of df equilibrium by dt into dt by dx, because we have a temperature gradient there. So, F equilibrium is a function of temperature. So, it is related to x through temperature, you understand. So, F equilibrium is not a direct function of x, but it is a function of temperature, and temperature is a function of x. So, therefore, we have split this as df equilibrium by dt into dt by dx. So, now when you say charge transport, so there is also going to be gradient of what? Yeah, voltage. Okay. So, you have the Fermi level EF is going to be a function of x. So, this Fermi level is now consisting of two things. One is your voltage gradient, that is one thing, that is the electrostatic thing, the other is the electrochemical potential. Okay. So, therefore, combination of these two will be your Fermi energy level. So, when you say there is a gradient of concentration, charge concentration, as well as there could also be a flow of electrons due to gradient of the electrochemical potential. Okay. So, together that means now df equilibrium will be a function of dx through your gradient of electrochemical potential, which is related to your Fermi energy level EF. So, therefore, it can be expressed as df equilibrium by def into def by dx. Okay. So, that is the first step. So, we write down as now df equilibrium by dx, but we can split this into df equilibrium by def into df by dx. What is the second term? Now, we also have an electric field or the Lorentz force term. So, we have minus E times the electric field magnitude in x direction, Ex by m, and what is the corresponding derivative? Df equilibrium by corresponding velocity in the x direction, dvx. Okay. So, this we can now write in terms of def and so on, we will do that. So, this is your starting point. So, I am just expressing this f is equal to f equilibrium in terms of this right now. That is the first step. So, where this is your Lorentz force f x. Now, can you write down the expression for the current flux? We will use the notation J for current flux in terms of Q for heat flux. Okay. So, this will be equal to in terms of write down in directly in terms of integral, that means you convert the summation into integral space for k. So, that is kx, ky, kz going from minus infinity to plus infinity, for example. So, what do you have for charge flux? You have minus E, you have Vx, you have F, right. So, this will give you the charge flux if you divide it also by, and you have dkx, dky, dkz divided by 2 pi by L the whole cube. Now, this will give you the charge flux or current flux. What is the unit of current flux? Ampere per meter square. Okay. So, from this point now we can use the density of states to convert all our integrals from the k space to energy space, because we can always relate wave vector to energy through the density of states. Okay. So, do that conversion and what do we get, and also you resolve this into a sphere and therefore cast this in terms of polar angle, azimuthal angle and energy. So, the three integrals kx, ky, kz gets converted into polar angle, as azimuthal angle and corresponding energy integral. I will use the subscript x to denote flux in the particular direction. So, therefore, you have 0 to 2 pi, 0 to pi and energy 0 to infinity minus E times Vx times F times, when you convert this through the density of states, you have 1 by 4 pi, you have sin theta d theta d phi d e. Please check this. You should be able to get to this point. If you are able to comfortably get to this point, that means you are understanding what you are doing. So, we are defining the density of states similar to the phonon density of states, except that instead of d of omega we have d as a function of energy here, E, right. So, therefore, similar to this we have, instead of h bar omega we have minus E Vx F, we have sin theta d theta d phi d of E d E. Okay. You should get a similar analogous expression. Is it clear? Everybody is able to reach this point, right? Any questions on this? So, now you can go ahead and substitute the expression for F. Okay. So, before we substitute, just let me call this as 1. Let us now express this in terms of the right functions. For example, as I said, dF equilibrium by dx can be expressed as dF equilibrium. Now, F equilibrium is a function of x only through the Fermi energy level, because this is what your Fermi Dirac distribution function, right, for electrons, and in Fermi Dirac distribution function F equilibrium is a function of E equilibrium and temperature. Okay. And when you say gradient, so your equilibrium distribution function now can be a function of x only through the gradient of the Fermi level EF. So, therefore, this is d equilibrium by dF into dEF by dx. Had there been a temperature gradient and no charge flux transport, this would have become dF equilibrium by dt into dt by dx, and there will be no electric field. So, then you will be able to get an analogous expression for transport of heat by electrons similar to that of the phonons, except that the relaxation time will be relaxation time for electron collision, not phonon collision. That is the only difference. Okay. Understand? So, this is how we also did this in the kinetic theory. The kinetic theory, you can consider whether these are gas molecules or these are phonon gas or these are electron gas. We get similar expressions, you have to only use the corresponding values of velocity of that energy carrier, relaxation time. Similarly, with the heat transport from the Boltzmann equation. However, when you are considering charge transport, you can isolate it separate from heat transport and say this is isothermal and derive the charge transport, because charge transport by itself is quite complicated. Now, you can also have a case where charge transport is happening along with heat transport, thermoelectric effects, Seebeck effect, Peltier effect, if you have heard about them. So, you apply a temperature gradient and there is a flow of current. So, there is a coupling of temperature gradient and charge transport. So, in that case it becomes a more complex function. You can also derive from the Boltzmann equation all the thermoelectric effects, including what is the expression for Seebeck coefficient and so on, in a very similar fashion, but again there F equilibrium will also be a function of temperature. Okay. Right now we are not assuming that temperature gradient is existing. So, to simplify the case. So, therefore, this is the relation. Similarly, if you are looking at dF equilibrium by dV x, how is it a function of Vx? Through which variable? Mu is your Fermi level, you can say that is your electrochemical potential mu. At 0 Kelvin, that is your Fermi level. Okay. So, that is function of x when you have a charge gradient. Now, what I am asking is what is the gradient in the velocity space, momentum space, through which variable it is a function? Definitely not EF. So, what are the other remaining variables? Temperature definitely not. Then E itself, because you remember the dispersion relation for electrons. We made a parabolic approximation E versus K, you remember. So, we have like this conduction band, valence band, hopefully you remember that. Okay, for metals your Fermi energy level is right inside the conduction band. Okay. So, therefore, we have made an approximation as a parabola and we have written the expression for E as, therefore, EC, we can say this is your starting of your conduction band plus half of h cut square k square 2m star. So, this is for the crystal. So, we call this as an effective mass of the crystal. This is not the electron mass. Okay. So, because h cut square k square by 2m comes from solving the Schrodinger's equation if you consider a free particle, but if you consider the entire crystal now, we have the effective mass m star. So, this is your dispersion relation for this particular approximation, parabolic approximation, and we can always shuttle back and forth between k and v. H cut k is nothing but mv, momentum. So, in the Boltzmann transport equation we can always rewrite this in terms of either k, gradient of k or gradient of v, we can always shuttle back and forth. So, therefore, we can simply express this as plus half of m star into Vx square plus Vy square plus Vz square. Is that okay? So, therefore, when you say now dE by dVx, okay. So, therefore, what will be the expression? M star Vx. So, when you therefore say dV equilibrium by dVx, so it is a function of Vx through dE, right, into dE by dVx, and this is what? M star Vx. So, now you can substitute this into F, therefore, this will become F equilibrium minus tau, you have Vx times dV equilibrium by dEf into dEf by dx. This is your first term. Second term will be, you have a minus Ex into, so there will be 1 over m and m star, these two will cancel off. So, you have dF equilibrium by dE. So, there will be so this m is actually m star for this case, this is the effective mass, okay. So, that cancels off. So, therefore, you have, let us call this as equation number 2. Yes.
So, is the Fermi level is actually particular for a quantum, for particular quantum number, its value is fixed.
Which one?
For that Fermi level of for first F equilibrium by del x is del F equilibrium by del Fermi level of energy. So, it will be very.
So, that will be fixed if you consider only equilibrium. If you have a non-equilibrium, so you are looking at different states. Now, you are having along x, different values of Fermi energy, then only there can be a transport of gradient to transport the electrons.
So,
you understand? So, when you are talking about, if you want to draw this now at different x, so I will draw Ef at x equal to 0, okay, and then I will draw somewhere Ef somewhere here. So, there is a gradient at, this is at x equal to x1. So, this gradient is the reason why electrons are moving from x equal to 0 to x1. In non-equilibrium case, therefore, Ef is not constant, it is now a function of x, right. Okay. So, now the remaining part is therefore to relate dF equilibrium by dEf to dF equilibrium by dE. How are they related? So, you write down the Fermi-Dirac distribution function, take the derivative with respect to Ef, take the derivative with respect to E. So, you have exponential of E minus Ef by kBt. So, how will they be related? So, they are, say you can say F equilibrium by dEf will be equal to minus dF equilibrium by dE, that is it, correct. So, you have a plus E, you have a minus Ef. So, therefore, you can also take the derivative and check. So, but without wasting much time, we will directly use this and substitute for F, you will be able to get F equilibrium plus tau Vx into dF equilibrium by sorry, make sure I am not making any mistakes here. So, this is dEf by dx plus Ex, I think some sign is a problem here, and I am taking dF equilibrium by dE. So, this is minus, correct, but this should be a minus here, right. So, this is dF equilibrium by dE. So, this should be a minus, just check that. No, that is fine. So, minus of minus is plus, okay, right. So, I take one minus sign out, so therefore, this becomes plus and minus of minus is plus, okay. So, is this clear? So, what I am writing is dF equilibrium by dEf, I am writing this as minus dF equilibrium by dE and substituting there and taking that common factor out, okay. So, if I substitute this into, therefore, the expression here for the current flux, okay. So, that will be the final step. So, I write down, therefore, J x, I can write this as minus E by 4 pi, okay. So, I can do this integral 0 to 2 pi, 0 to pi, 0 to infinity, and then I will have a V x square tau, and I also use the fact that integral over the solid angle F equilibrium will be 0, okay. So, therefore, only the second term will be here. So, I have dF by dx plus Ex times dF equilibrium by dE into density of states d sin theta d theta have sin theta d theta d phi. Okay. So, now V x will be nothing but V into V square, therefore, cos square theta. Okay. Now, again integral cos square theta, integral 0 to pi cos square theta into sin theta d theta is nothing but 2 by 3. Okay. You can just substitute that, and therefore, and also the fact that integral 0 to 2 pi d phi is equal to 2 pi. Therefore, you will be getting minus E by 3 times, now all these are not functions of E. So, you can take this as outside the integral over E plus E x, and you have 0 to infinity times V square tau d F equilibrium by dE d of V into dE. Right. So, finally, we have reached the point. So, this is the final step. Okay. So, now this expression is common to both metals and semiconductors. Right. So, for the case of metals, when you are applying only this to metals, we can assume that since you have so many number of free electrons, the number density of free electrons are too many, you can make an assumption that the change in the Fermi energy level is not that much, the gradient. Okay. So, we can put this to 0 because the number density is already too large. So, therefore, you may have some change, but it is not very significant because of the large values of electron number density. So, therefore, you can put this approximation for metals, and therefore, what you get for metal is minus E square by 3 E x tau V square d F equilibrium by dE d of V dE. Okay. So, this is your Ohm's law, provided you recognize that the way you write your Ohm's law is current flux is equal to electrical conductivity times the electric field. So, that means your sigma should be equal to minus E square by 3 integral tau V square df equilibrium by d d of E dE. So, this will be your expression for electrical conductivity. Okay. So, we will make one more approximation into this to make it much simpler, okay, and tomorrow we will complete that exercise. So, basically this is your Ohm's law, I mean except the fact if you want to write it in terms of electrical conductivity, we have the expression for electrical conductivity similar to the thermal conductivity. We write this as a function of the relaxation time of electrons, velocity and so on. Okay. In a similar manner you can also derive the expression for thermal conductivity of electrons. So, there you do not have any electric field, you have only temperature gradient. Okay. So, tomorrow we will make the next step here and then we will conclude this portion and then we will move on to doing some problems which involve the transport process in a small film, nanoscale film perpendicular to the film. So, this real time problems we will try to solve 1 or 2 of them, all right. Okay, thank you.